Good morning, fourth graders. I hope that this one works because the last one I recorded did not work. So we will see if this one works. We are talking about Module 3, Lesson 8. I can use patterns and arrays so that I can identify prime and composite numbers. This is something that's going to be important to you because it makes you, I think, feel more comfortable with numbers so that you understand numbers a little bit better. Let's look at our Khan Academy video.
Determine whether the following numbers are prime, composite, or neither. So just as a bit of review, a prime number is a natural number, so one of the counting numbers, 1, 2, 3, 4, 5, 6, so on and so forth, that has exactly two factors. So its factors are 1 and itself. 1 and itself. So an example of a prime factor is 3. There's only two natural numbers that are divisible into 3. 1 and 3. Or another way to think about it is the only way to get 3 as a product of other natural numbers is 1 times 3. So it only has 1 and itself. A composite number is a natural number that has more than just 1 and itself as factors, and we'll see examples of that. And neither, we'll see an interesting case of that in this problem. So first, let's think about 24. So let's think about all of the, I guess you could think of it as the natural numbers or the whole numbers, although 0 is also included in whole numbers. Let's think of all of the natural counting numbers that we can actually divide into 24 without having any remainder. We'd consider those the factors. Well, clearly it is divisible by 1 and 24. In fact, 1 times 24 is equal to 24. But it's also divisible by 2. It's also divisible by 2. 2 times 12 is 24, so it's also divisible by 12. And it is also divisible by 3. 3 times 8 is also equal to 24. And even at this point, we don't actually have to find all of the factors to realize that it's not prime. It clearly has more factors than just 1 and itself. So then it is clearly going to be composite. This is going to be composite. Now, let's just finish factoring it just since we started it. It's also divisible by 4, and 4 times 6 had just enough space to do that. 4 times 6 is also 24. So these are all of the factors of 24, clearly more than just 1 and 24. Now let's think about 2. Well, the non-zero whole numbers that are divisible into 2, well, 1 times 2 definitely works, 1 and 2. But there really aren't any others that are divisible into 2. And so it only has two factors, 1 and itself, and that's the definition of a prime number. So 2 is prime. 2 is prime. And 2 is interesting because it is the only even prime number. Only even prime number. And that might be common sense to you because by definition, an even number is divisible by 2. An even number is divisible by 2. So 2 is clearly divisible by 2. That's what makes it even. But it's only divisible by 2 and 1. So that's what makes it prime. But anything else that's even is going to be divisible by 1 itself, and 2. Any other number that is even is going to be divisible by 1 itself and 2. So by definition, it's going to have 1 in itself and something else. So it's going to be composite. So 2 is prime. Every other even number other than 2 is composite. Now here's an interesting case. 1. 1 is only divisible by 1. So it is not prime technically because it only has 1. It only has 1 as a factor. It does not have 2 factors. 1 is itself, but in order to be prime, you have to have exactly 2 factors. 1 has only 1 factor. In order to be composite, you have to have more than 2 factors. You have to have 1 yourself and some other things. So it's not composite. So 1 is neither prime nor composite. 1 is neither. And then finally we get to 17. 17 is divisible. 17 is divisible by 1 and 17. It's not divisible by 2, not divisible by 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, or 16. So it has exactly 2 factors, 1 and itself. So 17 is, once again, 17 is prime.
Okay, so let's take a look. And we just went over what a prime number is. So a prime number must be greater than 1 and has exactly 2 unique factors, itself and 1. The number 5 is prime because it has 2 factors, 2 unique factors, 5 and 1, and that's all it has. So let's take a look at our brain pop on prime numbers.
Hey, what's going on? You didn't say anything. Those are just beeps. Are you feeling okay? Wait, 2 beeps, 3 beeps, 5 beeps. I see what you're doing. Let me guess, 7 beeps is next? Man, I'm good. Dear Tim and Moby, what are prime numbers? Thanks, Giovanni. As you've noticed, Moby's been rattling off different numbers of beeps. Each of those numbers happens to be a prime number, which is a whole number greater than 1 that is divisible by exactly 2 numbers, 1 and itself. Put another way, a prime number can have only 2 factors. So 7 is a prime number because it has only 2 factors, 1 and 7. Okay, I challenge you to find a number other than 1 or 7 that divides evenly into it. Thought so. Okay, based on our definition, 1 can't be a prime number because it's only divisible by one number, 1. And a number like 8 is also not prime because it has 4 factors, 1, 8, 2, and 4. Numbers that are divisible by more than 2 numbers are called composite numbers. As for why Moby's beeping prime numbers, I'm not so sure. Communicating with alien civilization... Okay, you've been watching way too many sci-fi movies. The fact is, prime numbers have fascinated human civilization for as long as people have been studying math. We're pretty sure the ancient Egyptians knew about prime numbers, though the ancient Greeks were probably the first to really study them. The famous Greek mathematician Euclid wrote an entire book on the subject. He wrote about some of the most fundamental properties of prime numbers. Well, one of them was called the fundamental theorem of arithmetic. Here's what it says. Every whole number greater than 1 that isn't a prime number is actually the product of prime numbers. In other words, by multiplying different sets of prime numbers together, you can come up with any non-prime number, no matter how big or small. That's one of the reasons mathematicians continue to study primes. They're like the building blocks of all numbers. Breaking any number down into its prime elements is a process called prime factorization. Euclid also proved that there are infinitely many prime numbers. Trust me, they just keep going. Now, you might be asking yourself how we came up with all those numbers. There's actually a pretty simple way to identify all the prime numbers up to a certain point, and it's called the sieve of Eratosthenes. Eratosthenes was another ancient Greek mathematician who lived around the same time as Euclid. His technique for separating prime numbers from composite numbers is sort of like draining water from pasta. First, we make a chart of every number from 1 to, say, 100. Since 1 isn't a prime, cross it out. Then, circle 2, the smallest prime. Next, cross out every even number after 2. Since they're all divisible by 2, they're not prime. Okay, then circle the next prime, 3, and cross out every third number, since they're all divisible by 3. Then circle 5, and cross out every fifth number. Keep going until every number has either been circled or crossed out, and you've basically drained out all the composite numbers, leaving just the prime numbers behind. Of course, this only works up to a certain point. With bigger numbers, you'd eventually run out of space to write. Not really. There's no easy formula for generating prime numbers. The biggest prime numbers, numbers with millions of digits, can only be found using computers. These numbers are so big, it often takes hundreds of computers years and years to find them. As of early 2019, the largest known prime number is nearly 25 million digits long. There are an infinite number of primes, of course, so mathematicians are always looking to raise the bar. There are even competitions that award big cash prizes to anybody who discovers the next biggest prime number. No, you can't borrow my laptop for the next 10 years. Crazy robot.
All right. So let's take a look at what a composite number is, because we were really focused a lot on primes. A composite number is the number that has more than 2 factors. For instance, the number 9 has 3 factors, 1, 3, 9. So it is composite. 1 times 9 is 9, 3 times 3 is 9, and 9 times 1 is 9. Excuse me, 0 and 1 do not meet either definition, therefore they are neither prime, nor composite. So examples of prime numbers are 2, 3, 5, 7, 11. Just like that chart showed on the BrainPop video, these are numbers that only have 1 in itself as factors. Composite numbers are all the other ones, so I didn't list them. Let's take a look at our math journal page for today. And an easy way for you to find prime or composite numbers is to use an array. I'm sorry, I'm not sure why this logged me out. So hold on a second. All right, and I like to look at just one page at a time. So let's look at page 102. And let's make it a little bit larger. I'm sorry, I'm having some computer issues. So page 102 shows you up here, multiplication, identifying prime and composite numbers. Color an array to represent each of these numbers. So for 19, we always start with 1. Always start with 1. So if you're starting with 1 and you're going to draw an array that represents 19, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. That is the only array that represents 19. 1 times 19. How about 5? We have 1, 2, 3, 4, and 5. There are no other two numbers that multiply together to have 5 as a multiple. So 23 would just be 1 all the way to 23. So what do you notice about these? Let's take a look at our eraser here. It's not working. Okay. So what do you notice? What are some other prime numbers that you know? What are some composite numbers that you know? And how could you prove that a number is composite? Well, a number is composite if you can draw an array that is other than 1 times that number. So a prime number is a whole number greater than 0 that has exactly 2 unique factors, itself and 1. A composite number is a whole number that has more than 2 whole number factors. All right, so let's just try to get this to work, which is always good. So it would like you to color all the composite numbers, okay? All the ones that have more than 2 factors, okay, more than just one in itself. Circle those, or just circle them so you don't color them out. And then it says to color the matching array to prove that each number is composite, just like we did up here. I'm not going to have you do page 103 unless you really want to. It's a lot of busy work because it wants you to. In this, when you look at the finished graph or number chart, it looks very confusing. But if you choose to do it, that would be wonderful. So circle the number 2 and then draw this kind of a backslash through all of the multiples of 2. And what do you notice? Okay, and then it says circle the number 3 and draw this way forward backslash through all the multiples of 3. What do you notice? And then find the multiples of 6, and what do you notice? Down here it says circle the number 5 and cross out all the multiples of 5, 5, 10, 15, 20, 25, 30, and all the way down. Circle the number 7 and cross off all of the multiples of 7, 14, 21, 28, and so on. And then choose 3 numbers that have not been crossed out. And what are the factors? The reason I wanted to show you what this looks like is because it just looks a little bit confusing when you look at the finished chart over here. So if you would like to do that, that would be absolutely wonderful. So for your math journal pages today, the assignment is pages 102 and 105. And 105, I do not have a picture of to show you. 105 is just maintaining concepts. If I look in my math journal, 105 is ongoing math practice. So using the standard subtraction algorithm. And remember, we talked about the standard subtraction algorithm on Thursday. And if you have a 0, I want you to think about this. What do you need to do? We talked about the strategy of regrouping by borrowing from your neighbor. And then you need to write down some factors of different numbers like 18, 50, and 32, and 40. Okay, so that is going to be your work for today. I will post this on Classroom so you can watch this before our small group meet, or